Were there any questions? There were some questions about the lab report that we did for the lab last week, Le Chatelier's lab. We could take a look at that if you'd like. So I call this the fill-in-the-blank style lab report. So it depends on the lab. So for example, Le Chatelier's lab, we're just going to fill in the blanks here and then submit this form. The other type is a formal lab report or a formal lab write-up. The formal lab write-up is going to be for this synthesis lab that we're starting today. And there you're going to write a little bit more. I mean, I don't know if it's a little bit more. It's just in a different format than when you write for this. All right, so here, I just want the colors, like copper 2 sulfate, light blue, tetramine copper 2 ion, dark blue, just etc. So just fill in the colors there. And then here we go to explain the effects of ammonia and HCl on CuSO4 solution in terms of Le Chatelier's principle. Consider the following equilibria. And so this is CuSO4. Equilibrium. So we had copper 2 plus. The sulfate's pretty much just a spectator in here. We're just looking at the copper 2 ion. And then the effect of ammonia. Well, the effect of ammonia, the more ammonia we add, the more it shifts to the tetramine complex. And so we would write this here. And then all you need to do is something very simple. Should we do it in writing? Explain the effects. So increasing ammonia shifts right. Something like that. Increasing ammonia shifts it right. Color goes from light blue, to dark blue. Decreasing ammonia, but how did we decrease the ammonia? So we increase the acid. So increasing acid does what? Yeah, why does it shift left?
Because you're removing the base.
Yeah, so we're removing the base. So increasing increasing H plus means decreasing ammonia, which means it shifts left. Okay, that's done then. We're done with this.
That's all we have to do?
Yeah.
And I was stressing over that?
Yeah, a lot of people are stressing over it, but you don't have to do much. I mean, that's enough because, just explain what happens. So, we could write the reaction here, the chemical reaction. Here, that is H plus NH3 yields NH4 plus. And ammonium does not participate in this equilibrium. It's ammonia that participates.
Want to write that?
The reaction?
Yeah.
Sure, you can write the reaction there. Because that just shows you how I did it differently in class sometimes, Sometimes in class I'll do this. I'll draw an arrow here showing H plus going to ammonia, which removes the ammonia from the equilibrium. Part 2, equilibrium involving sparingly soluble salts, 10-11. What the heck is 10-11?
Run out the
Go. Yes, up. Right there. Yeah.
I need to get rid of this window here. You know how to get rid of this window?
Yeah, I think you push the little 3 lines on top.
All right.
Yeah, you click that, I'll get rid of it.
I usually use Acrobat. Alright, so the numbering system here, 10, 11. I think they're talking about,
There's 10 rings in the bottom.
okay, 10 at the bottom. So equilibrium involving sparingly soluble salt. So we just need to draw or write the equation out there. And so the equilibrium involved in 10 is we take the silvers plus the carbonates. How many silvers do I need?
2.
2, and then I'm going to form silver carbonate. Silver carbonate's an insoluble salt. Carbonates, phosphates, and chromates are all insoluble, so they'll precipitate. So all we say here is increasing carbonate is going to shift this to the, well, actually, that's not what they want there. Let's see what they have.
Just doesn't count for your observations.
Okay, 11 is nitric acid. Okay. So let's go back to the report sheet. Well, I don't know what they want on this line. I'm assuming they want the equation there.
What about this space on top?
It's for the cobalt.
Oh,
Yeah,
I skipped cobalt? Oh, yeah, I did.
And in the text, it says to, like for the average 10, 11, it says to write down observations.
Oh, write down the observations? Okay. Thanks. All right, so here, color of the cobalt 2 chloride, what was the color?
The color was. Which one?
Cobalt 2 chloride.
It was like a red, like a clear red.
Okay. Color after the addition of HCl.
Dark violet, clear solution.
Color after addition of water.
Back with recycle color, dark red, clear solution.
Okay. So, what was the equilibria here? So we had cobalt 2 plus HCl. Well, it's actually the H plus isn't doing anything. It's just the chloride doing it. And so it's just going to be the cobalt plus chloride. And then, how many chlorides do we have here? 4. It's going to form the tetrachloro complex of cobalt. 2 minus charge. And so the color of this is going to be cobalt chloride, COCl2, when we don't have excess chloride. When we don't have excess chloride, this is going to form just the cobalt 2 ion in solution. And this color was, you said maroon red, or what was it? Red? Okay, what was the color of this one? Violet?
It's like a dark purple.
Or dark purple? Okay, something like that, that's fine. And so here, what we do is we increase the chloride concentration. In this case, we increase the chloride concentration. Which direction is it going to shift? Yeah. So we just say shift right. And so the color should have became more violet. Okay, now how can we decrease the chloride concentration? Well, adding water, but adding water is going to not just decrease chloride, it's also going to decrease the cobalt 2. And so you say, okay, if it decreases the cobalt 2 and the chloride, it should shift left. But the problem is it also decreases the concentration of the product here. And so we're actually, if we decrease the concentration of the product, which way should it shift? it should shift to the right. So if we add water, then it's decreasing the concentration of the product, it should shift right. But on the other hand, it's decreasing the concentration of the reactant, so it should shift left. So do they cancel each other out? And it turns out they don't cancel, they can. You know, if we have the same on both sides, if we have the same on both sides, then there's going to be no impact. The same what? The same number of molarity on both sides. But in this case, we have different. And in other words, decreasing the concentration of which one, the reactants or the products, will have a bigger impact. Because we're decreasing, let's say we cut the concentration in half. Well, we're going to cut the concentration in half for everything. And which one's going to have a more significant impact will be on the reactant. So this is one way of thinking about this is increasing the amount of water is like increasing the volume. Increasing the volume favors which side? The side with more or the side with less? If you increase the volume, you favor the side with more or the side with less. If you decrease the volume, you favor the side with. So if you pinch down the volume, you're going to favor the side with less. If you increase the volume, you're going to favor the side with more. Which side has more? The less. So even though we're, by adding the water, what we're doing is we're decreasing the concentration of everything in there. And that's going to have a more significant impact on the left. We can show this by writing out the K expression. So if we write out the K expression here, the K is going to equal the cobalt, the tetrachlorocobaltate complex here, concentration over the cobalt 2 plus concentration, and then the chloride concentration to the 4th power. Now, if we cut the concentration in half for everything, this is just an example. So let's say we double the volume. If we double the volume by adding an equal amount of water, this is what we're going to have compared to the original. This is the original. The original is at equilibrium. And so if we double the volume of everything, that's going to be 1/2 times the original concentration of the tetrachlorocobaltate. And then this is going to be 1/2 times the original concentration of cobalt 2 plus. And then over here, this is going to be 1/2 times the original concentration of the chloride to the 4th power. Okay, so when we do this, this 1/2 will cancel that 1/2. So 1/2 to the 4th would be 2 times 2 is 4, times 2 is 8, times 2 is 16. So that'd be 1/16. In other words, it'll be 16 times here. So, for example, if we had equal concentrations, you'd see that the impact would be the same. So, for example, the complex here and the cobalt have equal concentrations, right? And so the impact is 1/2 the top, 1/2 the bottom. But here we have unequal. And so when we look at the bottom, we have this extra term. So 1/2 to the 4th is 1/16. Bring that to the top, it's 16. So this is no longer at equilibrium. It used to be at equilibrium here, but now it's 16 times bigger. Is that still, that's not at equilibrium anymore. Right? In other words, this has way too much product or way too much reactant. Way too much product, therefore it's got to shift to the left. And so this is the impact of the dilution. So this is not at equilibrium. If it's not at equilibrium, what we do is we call it Q, because when it's K, that means it's at equilibrium. And when it's Q, Q might be at equilibrium or it might not be. There are 3 different scenarios here for Q. If Q is equal to K, then, you know, what we did, or changes what we did, impact anything because we still have the same ratio. We would have had the same ratio if this term were missing. It'd just be 1/2 on the top, 1/2 on the bottom, and we'd still get Q equal to K. The Q is whatever we changed or whatever initial we're given. If Q is greater than K, that's what happened here. Q came out greater than K means we have too much product. Because Q is just the given ratio. Given ratio may or may not be at equilibrium. If Q came out less than K, then we have too much reactant. And so we don't want to call it K because K implies that it's at equilibrium. This is not at equilibrium. Does that make sense right now? We're going to talk more about Q in a little bit. Anyway, favors the side with more aqueous species. Right? It's like a gas. You know, when you increase the volume, you favor the side with more gas, more moles of gas. When you decrease the volume, you favor the side with fewer moles of gas. So we do that, fill that in. Did anybody already finish this? Or you guys finished it?
We're done.
It's okay. We'll quickly go through. It said they wanted the observations here. What do you guys put observations for number 10? Milky white color. What was it? Solid, liquid, gas? Milky white precipitate. So here you would just say milky white precipitate, something like that. 11? CCS, clear colorless solution. Okay, that's fine. Clear colorless solution, what you should say is that the precipitate dissolved. Is that what happened? Precipitate dissolved to form a CCS. Okay, so account for your observations. We could just account for the observations just using just reactions here, equations. And so the milky white precipitate was the silver carbonate, correct? Yes. And so we just have 2Ag plus carbonate forms the silver carbonate, Ag2CO3. Solid. Now, there are two ways to write the other reaction that happened. One way to write what happens when we add HNO3 plus HNO3. One way we could do that is via Le Chatelier's principle. Le Chatelier's principle is just going to say, well, the acid will react with carbonate. Carbonate's a base. And so if we take 2H plus a carbonate, what we're going to form is carbonic acid, H2CO3, which decomposes into H2O liquid plus CO2 gas. So pretty much we're just going to destroy the carbonate or consume the carbonate with acid. And what's going to result is if we decrease the carbonate, it's going to shift which direction? Left. Shift left, yeah. And so that should dissolve the precipitate. Alternatively, we could represent this just using a metathesis reaction here, and that would be B. Alternatively, we could just say if we take silver carbonate and react it with HNO3, what do we expect to form? We expect to form silver nitrate. Silver nitrate's AgNO3 plus H plus and carbonate. H plus and carbonate makes carbonic acid, H2CO3 which decomposes into H2O liquid plus CO2 gas. Then to balance this, we'll need 2 HNO3s and 2 silver nitrates. The driving force for this particular reaction is, which is the same for over here, we say in metathesis is going from a stronger acid to weaker acid. So stronger to weaker acid. And also gas formation. Gas formation is a driving force for metathesis. It's not a driving force for redox, though. And so we don't mix and match driving forces. We stick to, I have 3 categories of reactions because there are 3 types of driving forces. So, silver carbonate's a solid. Nitrate's a spectator, so essentially it comes out very similar. So those are 2 different ways we could, represent this particular reaction. Okay, is that clear for that?
Yes.
This will be due on Thursday, so you have more time. If more questions come up, you can ask me. So here's the net reaction of what we're doing in the synthesis, but this net reaction consists of multiple steps. And so let's take a look at the first reaction that's happening here. The first reaction is going to be between potassium dichromate. Now, tell me about what chemical property of potassium dichromate stands out. Like potassium dichromate. What's the first chemical property that you would think? Is there something where it's strong at? So you're thinking potassium dichromate. What's potassium dichromate good at? What is it strong? What's its strong points? What would you say? It's a good base? Good acid? What would you say it's good at? Strong oxidizer. Yeah, that's what it's good at. It's a great oxidizer. It's a powerful oxidizer. Once in a while you need to read that sheet, the redox sheet, and go through every one. Can you name everything in the redox sheet? If you can't name everything in the redox sheet, then you need to go back through it and make sure you can name everything in the redox sheet, because all those are just common, except for S2, the S2O8 or whatever that was. That one you don't necessarily have to name. But all the others, you should be able to name all the others. And so dichromate is one of the strong oxidizers, so you have to watch out, right? You need to watch out for this stuff. If you wanted to find out more information about dichromate, where would you look? on the bottle, or actually it's not on the bottle. The bottle doesn't contain that much information. It comes as an insert. When you buy potassium dichromate, you get it in a box. And in the box is the bottle of potassium dichromate, but there's also an insert. What is the insert that's included in the box of potassium dichromate? Yeah, close. Go with a try. Not the NSCS, the MSDS. Yes, MSDS. What does the MSDS stand for? All right, let me tell you something about, this is something I learned when I was a student, because when I was a student, I figured like, I kind of looked at all the tests I had at UCLA, you know, as I was a student there, and then kind of looked at the types of questions that were asked on the test. And I came up with a determination. In all my classes, it was like 90% recall of information. So if I could just recall what was said during lecture and write it down, I could get an A in the class, because 90%. And 10% was like challenge problems. 10% were like, they wanted to see, you know, if you're like special or something like that. You know, if you could answer these problems, then you stood out beyond the regular. And so recall, then I thought, okay, recall, if it's recall, then I want to make sure I can recall the information fast. If you have to think, you know, and think, then that's minutes ticking away on the test that you're losing, you know. And so the faster you can recall, which is just memorization, the better you are, and then you can just get that. And then so you want to be able to recall things, but as things pile up and you get closer to the test, you can't cram everything over, you know, the night before the test, because if you try to cram everything the night before the test, you aren't going to be able to recall anything, you know. And so you have to review. That's my advice. You can take it or leave it, but you have to review. You know, you have to review your notes. You have to review continuously. The MSDS is the old name. What's the new name for the MSDS? This is what I said earlier. There's a huge shift. I don't know why they did this. Don't ask me. Everybody had MSDS for years and years and years, and all of a sudden it was changed. Do you know what the new acronym is? SDS. Safety Data Check. And so either the MSDS or the SDS is fine.
Is that inside for the law?
Yeah, that's it. Materials. So we have some things here: corrosive, toxic, lung hazard, fire hazard. This is an oxidizer with an O. Oh, it's a powerful oxidizer. Be careful with this stuff. You know, but may make you want to rethink, you know, how you handle this. For example, sometimes I look over in the corner where people are weighing it out, and I see a dust cloud of orange, you know, and I'm thinking, gosh, it's bad. That's bad. One, well, signal word, danger. This danger, you want to handle this, may intensify fire. It's an oxidizer. Toxic if swallowed, harmful if in contact with skin, fatal if inhaled, causes severe skin burns and eye damage, may cause respiratory irritation, may cause an allergic skin reaction, may cause an allergy or asthma symptoms or breathing difficulties if inhaled, may cause genetic defects, may cause cancer. Have you heard of chromium-6?
Yeah.
Have you heard of Aaron Brockovich? There's a movie made about Aaron Brockovich. Maybe if you're not aware. Actually, the film probably the real Aaron Brockovich, but this is about groundwater contamination in Hinkley, California, which is in the Central Valley. And apparently, there's a whole bunch of chromium-6 in the water, and there was a big cancer cluster there. And she turned into an environmental activist. And I didn't. Well, I've never seen the movie though. No, I should watch that movie. But that's do you know what the oxidation state of this chromium is? Chromium-3 is okay. This is chromium, not chromium-3. This is chromium-6. So this is the stuff, you know, the Aaron Brockovich stuff. Dichromate and chromate both have chromium-6. Dichromate, this stuff is used in like tanning leather. And so a lot of like people who tan leather, or they use it in certain concretes. They have this in certain concretes and other stuff. Somebody was doing some concrete work next door, and this huge cloud of concrete dust came over the house. And I was just thinking, you know, there's probably quite a bit of chromium-6 in that. I don't want to inhale that. But it's like gasoline. You know, gasoline is also mutagenic. It's also carcinogenic. You know, when you're filling your if you have a gasoline vehicle, if you're filling your tank, you know, you don't want to inhale the fumes. Gasoline's a powerful reducer, and so a lot of these types of things can be said, you know, about gasoline. Causes damage to organs. So we just have to handle things safely to minimize the risk. And so in this particular lab, we do not want to drink, you know, or eat, you know, because in case somebody creates a dust cloud and some of that dust goes on your food or in your drink, you know, you don't want to get that or ingest that. We wear respiratory, use only outdoors. Well, we can't use it only outdoors. We have to use it indoors. And so normally what I do is I bring a balance into the hood, and then I leave it there. So right now it's over on the counter. I don't like it on the counter there. And so I'm going to take that bottle, put it in the hood, and I'll put a balance in the hood. You weigh it in the hood, and then you can transfer it over. That way we can minimize. You know, it's the transferring that creates the dust. You know, it's a fine powder, etc. And so we can read this. I mean, you know, a couple of hazards. It's a health hazard, and it's a powerful oxidizer. So we just want to be careful. But as long as we're careful, then there's no problem, you know, handling it. Because this is what we want to do. We want to develop skills so that we can handle hazardous materials or potentially hazardous materials safely. Okay, this being a powerful oxidizer, we don't want to mix this with the wrong stuff. You know, if you mix this with something like ethanol, which we're also using in this lab, that could create a bad reaction. But what we're mixing this with is this. What's this called? Not acetic. It's also, acetic acid is a carboxylic acid. This is a carboxylic acid as well. This is called oxalic acid. This is a dicarboxylic acid. It has two acid groups on it. In fact, this is the minimalist acid. So, you know, when I think of oxalic acid, what comes to mind? Is it a strong acid or weak acid? It's a weak acid, but it's on the stronger end of the spectrum. So it's a weak, you know, moderately strong acid, but not strong. And that's about it. You know, when you think about oxalic acid, that's pretty much it. But let's look at redox properties. For redox, would you call oxalic acid electron rich or electron poor? Or maybe, in the middle. In the middle? Well, what's the oxidation states? What are the oxidation states here? Oxygen's at -2.
Carbon's at plus.
Well, actually, we do hydrogen. Hydrogen's always first at +1. So we do that, and then oxygen at -2, and then carbon is at
+3.
+3. Good. +3, I would say that's kind of on the poor end of the spectrum or the rich end of the spectrum? On the poor end. And so if I were to guess, I'd guess oxalic acid is a mild oxidizer, Would it be a very good reducer? No, I think it would be a poor reducer and mild oxidizer. But do you want to react dichromate with a good reducer? No, so you want a very poor reducer. If you want to reduce, let's say what we want to do, this is the goal of this first step, is to take chromium, go from chromium 6 to chromium 3. That's our goal. We're not going to take it all the way to chromium metal, which is going to be chromium 0. And so if we want to reduce the chromium from chromium 6 to chromium 3, then we want to use a poor reducer so we don't get a violent reaction and have it explode in our face. And so this is good. We're going to use oxalic acid as the reducing agent. And what we're going to do is we want to, there are two ways we could do this particular reaction. The two ways we can do, we want to form chromium 3+. Chromium 3+ is just a standard, a monatomic cation. And then what's going to happen to the oxalic acid? Oxalic acid is going to be oxidized from +3 to +4. So if we take carbon from +3 to +4, what has carbon in the +4? CO2. So we're going to maximize the oxidation of that to form CO2. Like this. So this is what we call complete oxidation of oxalic acid. So CO2 is the product of complete oxidation of many organic. Oxalic acid is an organic acid, it's carbon-based, and lots of other organics. Alcohols, when you burn alcohols completely, what does it form? We do complete oxidation of alcohol. Water and CO2. If you burn sugars completely, what does it form? Water and CO2. So when we burn a lot of these organic compounds completely, CO2 is at the end. This is maxed out. It's maxed out at +4. All right, there are two ways we can handle an equation like this. One way is, this is what we call skeleton redox. A skeleton redox, this is back in chapter 5 of Petrucci, is we're given the major reactants and we're given the major products and we just need to balance it. Do you guys remember how to do these? What was the first step in balancing skeleton redox? Yeah, so we separated into half reactions, so let's go ahead and do that. The potassiums are going to be spectators here. Potassium ions, what are the chemical properties? Pretty much nothing stands out. It's going to be the dichromate. And so let's just get rid of the potassium, the spectator. We're going to look at dichromate going to chromium 3+. That's one half reaction. The other half reaction is oxalic acid goes to CO2. gas. Okay, so when we balance these, what do we balance first? Oxygen or hydrogen, or actually we balance other elements other than oxygen and hydrogen, right? And the chromiums here aren't balanced. We have 2 chromiums on the left. How many chromiums on the right? We only have 1, so how do we balance it? Yeah, we just put a 2 in the front there. Now it's balanced. Okay, then we balance what? The chromiums are balanced. Now we balance oxygen, right? And so over here we have 7 oxygens. This is the way I do it. I just set up a little table like that. And so I put 7 oxygens over on the left. How many oxygens do we have on the right? None. So how do I balance it?
First, you can't just have oxygen on the so you have to double the equation first.
Well, if we double the equation, then that's going to be a problem. Well, I guess if we double both of these, so we go 2, 4,
Yeah.
and then what?
And then you'll have an even number of oxygens. So you can do 7
We can't add oxygen because there's no O2 in this equation. That would be adding something we don't have in this equation. We don't need any O2 for this reaction to work. And so if we needed O2, then I'd have to get a tube and start bubbling oxygen in this reaction. But I don't need to do that, so I'm not going to bother adding O2. We add water. How many waters do we add? 7 waters. Okay. Then what do we balance? The hydrogen. So over here, I have 0 hydrogens on the left. How many hydrogens on the right? 14. And how do I balance out the hydrogens? I add what? I can't add hydrogen gas. It's the same thing. I'd have to get a tube, a tank of hydrogen, and then inject it in here. If I start injecting hydrogen gas in this, I'm going to get an explosion. Because the hydrogen and the dichromate are going to react violently with one another, and I'm going to have a huge explosion. We add. See, this is the reason why, you know, this recall stuff. This is why, if you're going to med school and you have to take the MCAT, are you going to remember this? Are you going to cram this in one night before the MCAT? No, if you're planning to go to med school, this is not the way to do it. You gotta keep your notes and refresh your memory because you're going to forget. Everybody forgets. I forget so much stuff. It's so easy to forget. This is why my friend, who I was trying to help, I told you, did I tell you about him? Yeah. This is why he had to take years off to go back and essentially retake everything. If you're going to med school, if you're not going to, if you don't use it, then, and you don't need it, then, just make room for other stuff, to remember. So we're going to add what? 14 H plus. We add H plus to balance that out. Okay, then we balance out what? Yeah, the charge. And so let's balance out the charge. But the charge is plus 14, minus 2 is plus 12. Over here we got plus 6. So how do we balance out the charge? Add electrons, and how many electrons into which side? 6 electrons to the left side. Okay, now it's balanced. We can double check its balance. Minus 6 plus 14 is plus 8, minus 2 is plus 6 and plus 6 match. Then we check the atom balance, 14 H's, 2 chromiums, 7 oxygens, so it's all balanced. And then we do the same thing over here. Doing the same thing over here. We balance which one first? Hydrogen, carbon, or oxygen? Not hydrogen, not oxygen, carbon. carbons, 1 carbon. How do we balance? Do I add carbon? So should I just sprinkle some diamonds on the right side? Let's add some carbon. That would be nice to put some diamonds over here and then to balance it. Or if you can't afford the diamonds, you can just add some graphite, you know, maybe get your pencil and start scraping some graphite off. Is that the way we're going to balance this? No, we can't add anything that's not there. So this one, we're going to add, we're not going to add anything. We're just going to change the coefficient. But then you're thinking, I just said that, but here I'm adding water. And here I'm adding H+. Why am I allowed to do that? Well, the reason we're allowed to add water is because aqueous solution, water, there's going to be a lot of water present. Most of that water is a solvent, but sometimes that water can be a reactant or a product. And the H+ is, well, we have to make sure we add H+. In this case, H+ is already there because we have acid present, so we're okay with H+. But if it wasn't there, then we have to add it. And H+ is okay to add. All right, so next we balance oxygen or carbon. So 4 oxygens, so it's balanced, so we don't have to do anything. Then we balance the hydrogen. 2 hydrogens, 0 hydrogens. And so we're going to add what? 2 hydrogen ions on the right. And then we balance the charge. So 0 on the left, plus 2 on the right. And so we need to add what? 2 electrons on the right. And then just check to make sure it's still balanced. And so 2 hydrogens, 2 hydrogens, 2 carbons, 2 carbons, 4 oxygens, 4 oxygens, 0 and plus 2 minus 2, 0. So it's balanced. So these are the balanced half reactions. Then we combine the 2 half reactions to get the full reaction. But actually, we'll just finish this here right now. So we have 6 electrons on the first half reaction. We have 2 electrons on the second. We have to get these balanced. So I'm going to multiply this one by 3 times this. So I'm just going to go ahead and do that here. So this is going to be 3, 6, 6, and 6. And then combine the 2. So let's go ahead and combine the 2 here. So I get 6 electrons plus 14H plus dichromate, Cr2O7, 2 minus, plus 3 oxalic acids. Okay, this is going to produce 2 chromium 3 plus 7H2O plus 6 CO2 plus 6H plus 6 electrons. Okay, now let's simplify here. The 6 electrons on the left cancel the 6 electrons on the right. We have 14H pluses here, 6H pluses here, so we'll get rid of 6. That gives us 8H pluses here. And then that looks like it. And so the net reaction here is going to be 8H plus dichromate plus 3 oxalic acids, 2 chromium 3 plus 7 H2O liquid plus 6 CO2. So we're going to bubble CO2 gas from this. And then we have to add excess acid. We have to add excess acid because we need some additional H plus in there. And so the limiting reagent here is going to be the dichromate, and we're going to add excess oxalic acid. When you do the masses don't have to be exact. Just make sure you have excess acid, oxalic acid in there. That's all. All right, any questions on this? Now, this particular lab, we're going to do individually. And so we're going to do it individually because you're each going to grow some crystals. And we'll talk about growing the crystals next time. Okay, any questions? All right, just a quick discussion here about this. So the heating step, we want to make sure everything dissolves, and then we're adding the oxalate. So what's going to happen is the chromium should now all be chromium 3+. We should have no more orange chromium 6 in there, correct?
Correct.
The next step is we're adding a whole bunch of extra oxalate in there. And so we'll need 3 oxalates for every chromium. And so this is going to give us the trioxalato. Complex here. Just going to have the 3-. So that's the next step here. So we'll heat it to boiling, and then we're going to remove it and then cool it. The final step that we're doing today is this. There were some spectators, so this is reaction 2. There were some spectators in there, the ions, potassium ions. Those are the spectators from the potassium dichromate and the potassium oxalate. And so we're going to take 3 of these and then have that combined with the trioxalato. This is wrong. Sorry. C2O4. Trioxalato complex. All right. Potassium salts are soluble in water, right? But what we're going to do is they aren't. At least this potassium salt isn't very soluble in alcohol. And so what we're going to do is we're going to try to make this less water-like and more alcohol-like. And so the more alcohol you dump in there, the less soluble this is going to be, and then this is going to precipitate. But we got to watch out because, you know, there's also potassium oxalate in there, and the excess potassium oxalate could also potentially precipitate out. And we don't want 2 precipitates coming out. And so we're going to add enough alcohol to precipitate out the green-black crystals. These are going to be green-black crystals of K3. This is with ethanol. Ethanol is abbreviated ETOH. And then we're going to have water in here. There's plenty of water. And so we're going to form what am I doing here? Cr C2O4 3 dot. How many waters of hydration do we have? 1 or 3? 3. So that's going to come from the liquid water here. Dot 3 H2O solid. And so that's going to fill up the void spaces in there. And so this last step is precipitation. So what you're trying to do with the ethanol, one, you don't want it hot, because it's hot, more things are soluble. So you want it at least room temperature or cold. To make it cold, we have an ice bath over there. And you want to watch. The thing is this. Crystallization is, you'll see a mix. What do you want? Do you want a whole bunch of tiny crystals or do you want a few big crystals? What do you think is better? Yeah, big crystals, because if you have big crystals, those big crystals have to be perfectly ordered. And being perfectly ordered, it keeps contaminants out of there. And so if we can get big crystals, the impurity is usually very high for big crystals. But the thing is, how do you grow big crystals? How you grow big crystals is you want to grow them slowly. And the point is, in crystallization, there are 2 processes that occur. There's a process called nucleation. Nucleation is growing baby crystals. If you grow lots and lots of baby crystals, you're going to just grow small crystals. So what we want to do is we want to nucleate just a few crystals and then have those grow big. And so when you add the ethanol, you don't want to just dump it in there all at once. Because what that tends to do is it tends to nucleate lots of little crystals, and those little crystals don't grow very big. And so we'll add the ethanol slowly so that we can nucleate fewer crystals and have those fewer crystals grow big. That's what we want. And so try that when you're doing this, and also other things that help. So first we're going to nucleate it, not in the ice bath. If you cool it down rapidly in the ice bath, you're going to nucleate lots of little crystals. So we're going to try to nucleate the crystals either at warm temperature or at room temperature, and then cool it to let those crystals that nucleated grow. Does that make sense? So crystal growing is a little bit of an art, in addition to science. So it's sometimes it's hard to grow big crystals. So some of you are going to get really tiny crystals. Some of you will get nice big crystals. So anyway, we're going to add some more steps to this later. What we're going to do is we're going to, cool it down a little bit, add the ethanol. It could be a little bit warm when you add the ethanol. And then you're going to look for signs of crystals forming on the bottom of the beaker. So, just tilt it one way or the other. And then cool it in the ice. If you don't see any crystals forming, that's fine. You just don't want any solids in there yet. And then get some ice water, cool it down, and then look for evidence of crystals forming. If you see some, that's good. Give it a little bit of time. But if you don't see some, you might add just a little bit more ethanol. A little bit more, meaning maybe twice as much. Now, what we're going to do is we want the crystals to grow nice and big. And so we're not going to force it to occur. So what we're going to do is we're going to use this stuff. This is called parafilm. Have you used this before? Parafilm is a wax paper. And so what we'll do is we'll take the cover off this. If I can. There's a cover sheet on this. There it goes, finally. And so you peel off the cover sheet, and then you have this wax paper here. This wax paper can stretch pretty much like double its area. But we're going to cut a piece like this and then cover our beaker. Just stretch it over this to provide a nice seal here. Now what we want to do is we want to let the crystals grow slowly. So what I'm going to do is I'm going to poke a little ventilation hole here so that some of the water can evaporate and some of the ethanol can evaporate out of here. And so as the solution volume goes down, it's going to get more concentrated, and then we'll start growing bigger crystals that way. And so I'll cover this like this and then just poke a small hole in the top here with something. Yeah, like a pen. That's fine. Go ahead. Yeah, something like that, or a couple of holes there. And then what we're going to do is we're going to leave this in our drawer to grow the crystals. All right, is that clear?
Yes.
Okay. All right, so next time when we come in, hopefully we have some nice crystals on the bottom of our beaker. Now, some of you already have a lot of crystals in there. Small crystals is fine. Small crystals, you can't really see the individual crystals. It's quite small. But what we need to do is we need to isolate the crystals, and we're going to isolate it using a Buchner funnel. This is a Buchner funnel here. Buchner funnels are good if you have a large amount of crystals, which we probably hope to have. And with a Buchner funnel, what we're going to do is we're going to use a piece of fitted filter paper, and it just sits right on the bottom here. And then usually what we'll do is we'll just spray a little bit of water so that it adheres to the bottom. And nothing can get underneath it. Just make sure it's well adhered. Now, to assist in the filtration, we're going to use a vacuum, our house vacuum here. So this is called a vacuum flask here. And we're going to hook this up to our house vacuum here. Our house vacuum is yellow. And it has a little bit of suction, not a huge amount, but enough to help. But we don't want to suck water into our house vacuum. If we suck water into the house vacuum, it will destroy our vacuum pump, if we get water in there. And so what we're going to do is we're going to have a trap In case water gets sucked, it'll get trapped in the trap and won't get sucked into the vacuum pump. And so this end, the sidearm end, goes into the vacuum here, so that if water gets sucked in, and this goes to our, this is called a filter flask here, or a vacuum flask. This stuff is nice to clamp. You know, if we get some clamps, then we don't have to worry about accidentally knocking it over. Okay, so if I accidentally get the water level too high so that it reaches the sidearm, then what's going to happen is it's going to get sucked into the trap, to the bottom of the trap here. And hopefully this doesn't go too high to get sucked into the sidearm and then get sucked to our vacuum pump. So this is just to prevent that from happening. And then we'll just attach this to the vacuum outlet here. Oops. And so it's nice to clamp everything, otherwise everything gets knocked over. Do you hear that? So it's a pretty decent vacuum here. We'll put that on there. Make sure we have a nice paid seal. And in this case, when you do vacuum filtration, it's very fast, you know. And so we'll filter. Do you see the water being sucked in there? Hey, it's hard to see, but there's water being sucked in there. All right, so what we're going to do is we're going to vacuum filter our crystals into the Buchner funnel. But the crystals are going to be contaminated on the surface with this solution. The solution's got excess potassium oxalate, excess oxalic acid. All the potassium dichromate should have reacted because that was the limiting reagent. And so what we need to do is we need to wash our crystals. When we wash our crystals, if we wash with water, that'll probably dissolve the crystals and then get sucked in here. So we're going to wash with alcohol. If we wash with alcohol, then that should wash off this solution here and leave us just with the crystals here. Okay, now your crystals might have come out really small, you know, tiny crystals, but what we're going to do is we're going to do this. Once we vacuum filter it, then we're going to take, you know, about half the crystals or more or less, depending on how many crystals we have, and then we're going to do a technique called recrystallization. What recrystallization is the purification technique where what we're going to do is we're going to take about half those crystals and dissolve it in a minimum of water. Okay, we dissolve it in a minimum of water so that we end up with a solution again, and then we're going to add ethanol to that and cool it to regrow the crystals. So each recrystallization step we do, we get purer and purer and purer crystals. So the ultra high purity stuff undergoes a number of recrystallizations. So they'll get the crystals here, recrystallize those, get the crystals again, recrystallize those, and each successive recrystallization, you have fewer and fewer impurities in those crystals. And hopefully with the recrystallization, we'll be able to grow some big crystals, you know, because, so we'll take half of those and then we'll do some additional things to try to minimize the amount of nucleation and maximize the amount of growth in our crystals. Does that make sense? So that's the plan. So so you're going to have to prep your notebook, you know, with the vacuum filtration apparatus and the remaining steps, but we're going to add a step. You know, the step before weighing it, what we're going to do is we're going to take half the crystals and then recrystallize. We don't care so much about yield for this particular lab. We can lose a little bit, and that's fine, but what we care about is purity. We want high purity crystals. And so if we lose a little bit, no big deal. But what we want are really nice crystals at the end.